Alright guys, welcome back. Until now we have learned different concepts of data modeling, and now it is time to turn our theoretical knowledge to practical example. First of all, we are going to discuss a business scenario and will establish an ER diagram based on it. Then we need to turn ER diagram to relational model so then we can import this model into a relational database. As we discussed earlier, relational model is required to be optimized with normal form activities in order to have a model including less redundancy and avoid transaction anomalies. Therefore, we are going to normalize our relational model to 3NF form, then it will be the best fit for our OLTP system. Finally, on top of the OLTP system, we are going to build a data warehouse which includes the dimensional model based on facts and dimensions. So let's consider our example scenario. There is a company that produces different type of products, and these products are sold from different stores, maybe which are in different locations or cities, and customer would visit the closer store to her and would purchase different type of products. For example, the electronic products like phone, tablet, headset, and at the same time she can also buy some beauty products like perfume, lipsticks or nail polish. So she's gonna do one-time payment for all these purchases, so they will be all documented in the same invoice. So in this business scenario, let's define what kind of entities we have in here. As you remember that entities are the basic objects of the ERD, so we can assume them as nouns. So we have the customer and they buy products by doing an order from the stores, and these products may belong to any specific category like electronic or beauty. So obviously we have 5 entities in here: customer, product, product category, store and order. As we find out the entities now, we can start to build fundamentals of ER model. As you remember, as a first step of building ER diagram, we set up entities which we already mentioned as customer, product, category, store and order with these rectangle shapes. So now it is time to look at what kind of relationships there is between these entities. Customer would buy a product from store. It means there is a relationship between customer, product and also store. And this relationship is provided by the act of buying. In a way we refer to it also as ordering. So look at the first relation between customer and order. So customer may place one single order from a store, or she can visit the same store in different time of periods and would also buy different products. So it means that one customer would have many orders and there is a one-to-many relationship between customer and order. So when we look at the relationship between order and store, it is quite obvious that many customers visit the store and do shopping. So one store may include multiple orders from the same and different customers. So the relationship is also one-to-many. But what is the relationship between order and product? As we mentioned that a customer may have one order or many orders done in different point of times. And the specific order of a customer would have single or many products. So it means that customer would visit a store and buy multiple products and pay them all in once. So single order would include one or many products, and she can do it anytime when she wants. And on the other hand, a specific product will take place in more than one order. It means customer A and B both can buy telephone, so the product of phone would be included in both orders of these different customers. That is why one order would have multiple products and the product will show up in more than one order. So there is a many-to-many relationship in here. And the last relationship is between product and category. So it is well clear that there will be multiple products in a specific category, as we already mentioned that customer would buy tablet or phone which belongs to electronic category, and also perfume or lipstick that is contained in beauty category. But a specific product would not occur in 2 different product groups at the same time. So there is a many-to-one relationship between product and category. So the remaining part is defining of the attributes which describe the entities, as customer name, surname, email or address are the main characteristics of the customer. And we have also other attributes for category, product and store, as product name, store name or category name. So we also have details of the order, as what is the order ID and when it took place. And differently in here, you see that we have also attributes for the relationship between order and product. So what is the unit price or quantity of a specific product which is purchased in a specific order? So now we transformed our business processes to ER diagram, and as a next step, we need to turn it to relational model in order to be able to import to a relational database. So in here, I'm going to use the diagrams.net. It is a software development tool that helps me to create my diagrams. Okay, I'm going to create a new page. So then create a new diagram. Also pick the entity relationship diagram. Then I'm going to use the root folder. I'm going to just delete these existing ones. Okay. I also copied my ER diagram to a different page. Then I will take it and paste it to my existing screen. Okay, first let's define the tables which we use for entities, and we will also set the attributes inside them. I'm going to pick the entity relation, then also pick the table structure. Okay, first I'm going to enter the customer table, which is based on my customer entity. Then I will also define the primary key field. This is the customer ID. I can also use underscore. And additional attributes, which is the first name and also the last name and email. I can add the additional rows from here. Okay, I need two more additional rows. Okay, let's enter the postal code. And also the final one is the city. Okay, then I finalized the physical table of my entities, customer entity. Then now I'm gonna create the other tables for other entities also. Let's create a new table for store. And also the store ID is the primary key field. And also the store name are descriptive attribute. Then we can remove these rows that we don't need them. So one more table for the product entity. Again, we have product ID as primary key. Then we have product name. And we have also one more table for the category entity. Again, the category ID is the primary key. Then we have also category name as descriptive attribute. Okay, so we have created the tables for customer, store, product, and category. So we are missing the order one. Let's create also the last one. Okay, this is the order. And the order ID is the primary key. And we have also the characteristics of the order date. Okay, let's type it. Okay, let's do some reorganizing on the tables and bring product and category to closer. Then also the order between customer and the store. Okay, now seems a little bit better. So now look at the relationships, how we are going to define them. First relationship is between customer and order. So we have one-to-many relationship between them. So it means that customer would have multiple orders. So maybe you remember that when we defining the relationships. So we will pick the primary key field of the customer, which is customer ID, and insert it into the order table as a foreign key. So we have again the similar step for the store and order relationship. Because there is a many-to-one relationship between store and order, it means that in the same store there will be multiple orders. So we are going to pick the primary key of store ID from the one side and insert into the order table, which is the many side, as foreign key. And when we look at the diagram, and lastly, we have also one-to-many relationship between product and category. That is why we are going to get the category ID field from the category table and put into the product table as a foreign key. And we will remove the last row that we don't need it anymore. So look at the diagram again and to see what is remaining. So, and finally, there is a many-to-many relationship between product and order. So it means that one order can have many products and one product may exist in different orders. From earlier session, you may remember that we solve many-to-many relationship by using bridge table. And bridge table include the composite key. In general, composite key means that it is a primary key composed of multiple columns used to identify each record uniquely. In our scenario, combination of order ID and product ID primary key fields compose a composite key and identify each unique record, and we will name our bridge table as order detail. And additionally, we are not going to use the composite key as a unique identifier in the order detail table. Instead of it, we are going to create our own primary key. So that is mean order item ID. So you remember that there are descriptions which are depends on the relationship between order and the product. So it means that in a specific order, what is the unit price of a product or what is the quantity number? So that is why we are going to insert the descriptive attributes of this relationship into our bridge table, which is the order detail. And now create also the relationship between tables. So with customer and order, we have one-to-many relationship. And for store and order, we also have one-to-many relationship also. So the side of store is 1 and the order side is the many. And we have also one-to-many relationship between the category and also the product. So in one category, there will be multiple products. That is why the product side is the many and the category side is the 1. So there is always one-to-many relationship between the source table, and which is in here, it is order and product, and also the target table, which it is a bridge table. So it means that one order can have multiple products and the order ID is repeated in order detail table, and also that one product can show up in multiple orders. So that is why the product ID is also replicated in the order detail table. So we are going to create one-to-many relationship between order and order detail, and also the between product and the order detail table. So now we transformed our relational diagram into the relational model. So let's make it a little bit nicer. Okay, now we turn entity relationship diagram to relational data model. As you remember, in order to support fast write operations and to reduce the redundancy, we need to normalize the data model with normal form activities. But before deep dive, I just want to have a short reminder about the normal form rules. In the first normal form, a column cannot hold multiple values. Actually, in this example, we don't see the records inside the tables, but we assume that multiple values are not stored in the same column, and we comply with the first normal form. So in the second normal form, when the primary key value is not able to identify each record uniquely, it addresses us the usage of the composite key. For example, in the old example we earlier discussed, the student is registered for more than one courses, so student ID is repeated. Therefore, we need the student ID and course ID as a composite key to make each record unique. But as you remember, in second normal form, we try to avoid composite keys. So we had the similar scenario in earlier session and we talk about them. So the composite keys mostly occur when there is a many-to-many relationship between two entities. And to solve this, we use the bridge tables. So in our sample, we already inserted the composite key columns as order ID and product ID into order detail table. So we already aligned with the second normal form by creating order detail as a bridge table. So now have a check if we are also aligned with the third normal form. Third normal form tells that we should avoid the fields which partly dependent on the primary key fields and also dependent as well as the other columns. For example, store, product and category tables include the name fields as an attribute, and this value is fully dependent on the primary key, which is the ID field in here. So when the product ID change, the product name also change. But when we look at the customer table, the first name, last name, email address are the fields dependent on the primary key field. It means that when the customer ID changes, customer name would also change. And even the two customers has the same name, still they are different customers for us. So customer ID is the identification for these fields. But when we look at the city information, it is partially dependent on customer ID column and as well as the postal code. So when the postal code changes, then the city name would also change. Therefore, this field does not comply with the third normal form. That is why we need to separate it into a different table. First of all, we are going to create a table. Then we are going to rename it as postal. Then we are going to define the primary key as postal code. So we can also create the system generated primary key, which is different than postal code. Then we will enter also the city information, and we are going to delete the rows which we don't need. Okay, we're going to also remove the city information because we already included it into the postal table. So now the postal code became the foreign key. Then there is a one-to-many relationship between postal and the customer table. So it means that in one city there will be multiple customers. So now our relational model is also normalized and we get rid of the redundancy and it is ready to be imported to our OLTP system. On top of the OLTP systems, due to reporting and performance requirements, we need a data warehouse platform which emphasize the fast read operations and support the complex queries. We also mentioned that the Kimball dimensional model became prominent when we talk about data warehouses approaches. So that is why we finalize our example by transforming 3NF form to dimensional model. To create a dimensional model, there are a couple of steps we need to consider. The first step in dimensional modeling is identify the business objective. In our example, the business objective is to store the information of how many products bought from single store by a customer. Then we will identify the granularity, which means that the lowest level of information stored in the table. If the table contains daily sales data, then the granularity is the daily. In our example, a specific store sells multiple different products in a single day to different customers. Therefore, combination of product, date, store, and customer is the lowest granularity for the fact table. The granularity of the fact table also determines how much storage space the database requires. You must carefully determine the granularity of your fact table because too detailed granularity could result in an astronomically large database. Conversely, too higher granularity could mean the data is not detailed enough for users to perform meaningful queries against the database. Then the third step, we will identify dimension and its attributes. Dimensions are objects or descriptions to provide information about the facts, and they are associated with fact tables via foreign key columns. In our example, we are dealing with the product, customer, and store, and they are the dimensions tables for us. So let's define the dimension tables. I'm just gonna copy the tables that we use in the 3NF model and rename them. So let's copy the store table. And then we will rename it as store dimension. But in here, we don't need further changes. Okay, let's move on the product table. Then copy it from the 3NF model that we have created earlier and rename it as dimension product. As you remember, dimension models are denormalized structures. Therefore, we integrate two separate small tables into single table. There are a couple of points we need to consider when integrate attributes from two tables. Both attributes logically belong to the same business entity, for example, the city or the region of a company. Or both attributes have a strong relationship, like one-to-many. And also both attributes naturally appear in the same hierarchy. For example, product and product group. So in here, we have hierarchical, also one-to-many relationship between product category and product. Then we can combine them into a single table. So remove the category ID foreign key field, and we're going to insert the category name attribute. And as next, we will copy the customer table and rename it as dimension customer. So we will keep the existing attributes as first name, last name, and email, and we will combine it with the postal table as both attributes logically belong to the same business entity. So in here, postal information simply tells us where customer lives in. So we are going to insert postal code and city information back to customer table. So let's remove the foreign key identifier from the postal code and also enter the city information. Instead of star schema, we can also use Snowflake model and keep separating customer and postal tables. Okay, now as last step of dimensional modeling, we will define the fact table. As we discussed earlier, fact table holds the keys which reference to dimension tables and something that is measurable. So let's create a new table for a sales fact. First of all primary key fields from dimension tables will be inserted as foreign key into the fact table. So in here, we have product ID, customer ID, and store ID fields will be added to the fact sales. Then the remaining metrics like unit price and quantity are our measures and also belong to the fact table. We have also one remaining attribute in here, which is the date, and that describes when the purchase took place. So we are going to create a dimension table for date and reference it to the fact table via foreign key. For a dimensional modeling in data warehouse, there is a need to ensure that every fact table has an associated dimension table. So let's create a dimension table. Then define primary key field for this table as date ID and insert valuable information as day, month, and year. Then insert this primary key information to fact table as foreign key. The fact table also has primary key, it means the composite key, that is combination of these four foreign keys: product ID, customer ID, store ID, and date ID. But instead of it, we can also create a system-generated primary key for the fact table that we are going to insert a sales ID which identify each record uniquely in this table. And the relationship between dimension tables and fact tables are one-to-many. So dimensions tables is the side of the one and the fact table is the side of many. Because sales records can be replicated in fact table by the same product, store, and customer. So our dimensional model is completed, and lastly, if we want to track historical changes about one of the dimensions, for example, if the customer moved from one city to another and we would like to record the changes, so we can benefit from slowly changing dimensions by adding start date and end date fields into customer table, which stores the time intervals of customer to being in different cities. And we also need additional surrogate key column instead of using the customer ID as primary key in order to define each record uniquely. So additionally, in this scenario, we need to also insert the surrogate key columns from dimensions to fact tables instead of using the natural keys, which are the customer ID, product ID, and store ID, in order to provide relationship between dimension and fact tables and the show of transactions which take place between these time intervals defined in the historical dimension tables. So we started to define a business process and created our relational model based on it. Then we transformed it to relational model which is suitable for relational databases. But in order to make it suitable for OLTP systems, we use optimization techniques and turn to 3NF form and also finalize our model with a dimensional model. So I hope that gives you a better understanding about all theoretical parts that we have discussed so far and bring together the pieces and see the whole story. Thank you for listening.